Okay, so what we're going to be discussing now is just this particular slide here. I'm going to try to go through it just a little bit, and then we'll kind of go over to the R code to give us an idea of exactly what we're doing here. Okay, so in this case, I was discussing the Logit on the previous slides, but remember what I told you, that basically we're just changing the link function if we change from Probit to Logit. And for now, what we're looking at here is our standard LPM model that we know that we can look at the coefficients to get an idea of what the overall effect is on, in this case, I'm still using the spam example. So basically, what characteristics are most likely to give us a probability of success for identifying spam emails? In this case, I used the log of the number of characters. Basically, it's a dummy variable if it's to multiple people, not just me, but multiple. How many? If it has an attachment or not, dollar signs or not, whether it's telling me I inherit to something, and then Viagra in there. From that, I just have 3,921 observations. Remember, I told you that R squared is not really as meaningful in this type of model, but it still will produce one. Okay, so keep that in mind, but it's not really what we think of as really being a best fit. Okay, what we're more interested in here, so these are the models we're looking at, is basically a logistic and Probit. Now, if you look at all the signs, you're going to see, for the most part, that those signs match what we get in terms of the LPM model. And it's the same thing for the Probit here. So this is what I meant by, when we're looking at these, that we can tell the direction or whether it increases or decreases the probability of success. So in this case, if I was looking at the number of characters, the larger the number of characters, the less likely, or so in this case, this is the log, so it's basically if we're increasing it by a percentage, and we have, well, I don't want to get into the interpretation right now because it's a little bit funny, but basically, if the number of characters is going up, it reduces the likelihood that that it is spam in this case, or the probability of it being spam. Same for being within multiple people. So I found this actually kind of funny on the multiple people, because I was thinking that sometimes in these emails, so the spam emails they send out, basically you're blind copied in it. So basically you couldn't tell if it was to multiple or not. But I thought when I was originally going to run this, it was going to show it as being insignificant. But apparently it's picking up another way of looking at it. Okay? And then so forth. We can even look at attachment. So that actually, if there's an attachment, it's more likely to be a spam. So sign we can tell, and that's generally okay. But a lot of times we want to tell how much is increasing the probability of success or decreasing the probability of success. You know, what is that overall factor or probability? So this is how we would run these, but basically I want to show you some of the R code as well so that we can kind of get which exactly. So in this case, the package that we're going to be using is the, actually, which is the package for that? Oh, it comes in the base package, is what I thought. So it comes in the stats package. But basically, if we type in GLM, then we can basically get how we're supposed to formulate these particular functions. Basically, we have their equations. But then there's a lot of other choices here that we have to actually choose, you know, what family it comes from. GLM is not just Logit and Probit. There's a lot of different models that fall within this system. So if we go a little bit further down, you would then find a few more bits of information in terms of how we could structure this in terms of weights, as well as with, let's see, here we go, in terms of family. So basically we need to give it some idea. But the thing is that this becomes very important because it's no longer just OLS, we don't care about the distribution. Here, we have to let it know exactly what it is, or at least have an assumption about what it is. In this case, because it's going to be feeding it through the link function. In this case, we have the family, and then I could click on that to get an idea of everything that's possible for choosing. I think these are generic, and I'm not sure if they're specific. Let me see. Yeah, okay, these are all used for the GLM functions. That's good. So we can look at the Logit, identity, inverse, which typically is the gamma distribution. We also have inverse Gaussian link, Poisson, quasi, as well as a few others around here. These are all possible choices. Okay, I'm going to go ahead and say this now, but we're going to, because I might forget to tomorrow. In these functions, some of them can be used for panel type structures. Others, not so much. Okay, so when we talk about panels, or at least short panels tomorrow, we're going to talk about a few of these that we can, I don't want to say tweak, but we can basically, in some ways, making a few assumptions or a few adjustments, basically allow for this unobserved heterogeneity from the panels. But it's not; these aren't things that are straightforward all the way across all models. Okay. But these are all the choices that we can actually get within these models for the GLMs. Yeah.
So the GLM is not necessarily any package we have to install on our.
It comes through the stats package, which is a base package, so it's already in there. Now, I'm using that right now, but there's actually a bunch of different GLM packages. So one that I'm going to kind of introduce tomorrow is more designed for panel structures. So it comes under, they always shorten the names of these. I feel like I'm saying them wrong, but I call it the Fixit, but it's basically FIXEST. And it falls within a certain, some of the GLMs that can be used for panel type structures is in that package. But this is just one, like I said, there's always, for each type of system that I know, usually you can find at least 5 different packages doing some type of adjustments. So it's not saying this is the only one. Is there a particular one you were thinking about, or just wanted to know if it's already in the base package?
I was just trying to figure out if it's there already, and if like, I know sometimes you have to. I know you said it's not, you don't have to store it like the Woodbridge data.
Mm-hmm.
So I thought maybe it was something similar to that, but it's not.
So there's one, this one is just like the base, but there's a few things I can't remember all the packages for it, but there are ones that are a little bit better when it comes to slightly modified structures, or dealing with factor variables, or making sure that when we ask for robust standard errors, it actually is robust. There's a few, I'm not getting into all those details, but there's a few things that, different ways of handling certain assumptions that it makes in the model. So this is the base, but I would definitely go out there and look for other ones that might be newer type adjustments. Like I do know one, I think it's in R, or it might be in, I'm pretty sure it's R. And I think it's called GLM2, just to give you an idea. Just make sure that's right. Let's see. Yeah, GLM2. So this one is a little tweak on the GLM package, in the sense that it's made for, if I remember right, oh yeah, that's what it is. It's basically has a little bit more stability, because remember I told you these are not models that typically use calculus. What we're doing is we're using maximum likelihood estimations. But in doing that, we know that or if you know anything about the models, sometimes those models don't always converge. They use different procedures and methods to actually help with the conversion. Over time, we've gotten a little bit better in creating the algorithms that do the calculations to make them a little bit more stable. That helps with a lot of different things in terms of speed of the package, whether it converges. So that's why I always look for newer type packages that might improve on the base. So that's where it might be helpful to look. I specifically was having to use this one because I had a high dimensional Logit model that basically kept failing because it was just, the old algorithm just wasn't working very well with that data. As soon as I plugged it into this, it was done in less than 5 minutes. So it benefited me that way by knowing there's additional packages. Okay. Okay, so in this case, is this the right one? Yeah. Okay, so once we have the command that we're going to be using, so the first one we already know it. We know it's lm for OLS. And I didn't say this the other day, but sometimes, especially in programs, you have to actually generate the log variable and then you can use it. In this case, you actually can just tell it to log within the equation itself without having to create it first if you want to. Okay? And then you'll see that the structure for the GLM is very similar. Okay? We're taking those linear functions and basically just using it and then adding a few additional things. In this case, I'm telling it to use the family of binomial with the link function of a Logit. Okay? And then you can see the only difference between that and the Probit is that I'm basically changing the link to Probit. Okay? That's just telling it how do I get it back into something that I can use. Okay? And it's just an assumption on my part. Between these two, you're not going to get a lot of difference. Like I said, they're going to be very similar near that mean. Away from the mean at the tails, you're going to get a little bit more difference, a little bit more action on some than others. Okay? But it's relatively straightforward. I mean, as long as you tell it, you know, here's the function, GLM, and then it's just you have to add this little portion here. You know, the global options and where I changed the color of the background? There's a little thing called a rainbow tab, which tells me how many tabs I go over. It's not as important for the R script, but if you start using RMD files, tabbing over is important because it can basically change how the itemization is. Like here, you have to know how many tabs it goes over. So it's not important for the R code, no, not as much. It's just mine highlights how many tabs I'm over because I need it for my RMD file. Okay. But you can turn it on or off relatively easily in your, as you change those visuals, there's a lot of things you can do in there. That's just one of the ones I do. Okay. So you can see that it's relatively straightforward. So we run the models, we get our coefficients, we hopefully are happy with them for the most part, and at least we can know the sign of what the direction. And like I said before, those signs, hopefully, because we're getting a lot of the same information from the LPM, from the Logit, and the Probit. The signs should all match. Okay. The reason I say should is I've seen it in a book one time that says it said should. I've never seen a case where it didn't, but I haven't seen every single model out there that's been run. Okay, so it should match. And you'll notice also, for the most part, you're going to see very similar effects across most of the covariates in terms of significance. So, you know, one thing's significant, the others usually are, but it's not always the case. This is one of those cases. Okay? The sign matches, but the significance, not so much. This is where I was telling you that it should give you the same answer, but there might be little bitty differences just to how the data is set up. It also might mean that basically this is not the way this original model was supposed to be run. Okay, it could have been they could have been trying to do it in a different way with different covariates. So the coefficients in this case, I've already sort of went through this, but I'll go through it again. What does the actual coefficients mean? Basically, the sign indicates the direction of the effect on the probability of success. And I say they should match the LPM. And we note that the coefficient or estimates are not the effects of the covariates. And that's why I say, well, not directly. Remember, I told you, in the Logit, those coefficients are affecting the log or the odds ratio. In the case of the Probit, it's affecting the z-score. And that's where we're going to do a little bit more later on that. So for each observation, we estimate the predicted probability. So we can go ahead and pull out something called a propensity score from this. But again, we do have to take it a little bit of step that we need to know what that link function is. That propensity score is going to depend on our assumptions. So this is, in this case, the F, because if I was using the logistic, the F would be the logistic, and if it's Probit, we'd be in the normal CDF. So these are our estimated coefficients, and then we have our X vectors. Our vector of covariates here. And then our predictions will be bound between 0 and 1. That means we don't have that LPM problem. It's not above 1 and less than 0. And so we can also use these to sort of see how our model ranks observations. So who is the more or less likely to have a y equal to 1? Again, under a condition. Look at how this is. So we have this linear outcome here. And I say it's feeding to a function. But the problem is you'll notice that the x and betas are there. We predicted, or we got the coefficients, but they're all multiplied by an x. Okay? That means there's going to be some choices that we have to make here. And once we make those choices, then we can rank. Before that, we can't. Okay, so this is where those extra choices come in. That basically we can rank once we actually choose portions of x. I can choose the mean, and then once I choose the mean for everything, then I can rank them. If I choose another outcome, it's going to be a different rank. Okay? So it's still not the effect of the determinant. Okay? The propensity score is not the effect. We're only about 50% of the way there. Okay? But we are getting closer. So as you can see right now we can run the models, we get the coefficients. We can go about finding direction. We can go about trying to figure out how to rank them, given certain choices on our part. But still, we're not to the point that we can use or compare that back to what we get in terms of OLS. Okay, we don't know that as of yet. Okay? But just to give you an idea, if I was to choose a point, in this case, if I was to choose, say, the mean across everyone, then once I do that, I could actually get at my predicted probabilities, and then I could compare them across, well, propensity scores in this case, across the log of, say, number of characters. This is what I meant by basically the sign is telling us something. So the LPM says it's a negative. So basically the more characters in that thing, the likelihood of actually predicting probability of success is falling. The same for what we get in terms of the Logit and the Probit. So that's good. But at the log of the number of characters, as it's going down, we see that we're going to predict higher probabilities in terms of the Logit and Probit at this point. They're following each other, but that's a big difference between what we got in terms of LPM. But around the average, I'm not going to say this is the average, but somewhere around in this area, if that's what the average is. I never checked what the average was. Maybe that's because we're following in that point where they're all kind of meeting. And then we're getting very similar effects. This is what I meant by the fact that we can actually, if we only care about the average, it might be good just to give a test. Because I can tell you, the LPM in most cases, even with large data sets, a few minutes to run, max, even if you're in millions of observations. Logit or Probit with 1 million observations, you just go get your lunch. It still might not be done by the time you get back. It's going to be a lot more complicated process. It's possible it might finish very quickly. There's always a possibility. But at the same time, if there's any type of convergence issues, any of those things, it's going to take a little bit. Okay? So that's why if you're just wanting a quick check, that's why I'm saying LPM. You know, are my right-hand side variables working? Are they sort of giving me something that's, you know, understandable and maybe meaningful economically? You know, those are the things we can get real quick with the LPM before we go to the more advanced models. Okay? And I could do this across any of the other characteristics that we looked at. So you'll notice I put a practical here. But again, like I said before, I'm going to work through all these with you today. Okay? Because some of you might be pushing into these types of modeling strategies. And it's mainly that you get you start to get the base, which is what we're doing right now. And then we're going to sort of slowly walk through all the sort of steps that we're going to kind of do as we're trying to run these. Okay? So, or I can give you like 10 minutes. I don't know. Do you want a complete walkthrough, or do you want to try for 10 minutes and then do it? Who's the brave one? Okay. Okay, so what we're going to do here is we're going to use the Mirage data set again, just to keep it simple. But we're going to use a different version of it. Before I was using, I believe, the cross-section. Now I'm going to be using the panel version of it. Okay? So a lot of the stuff is still going to hold for what we're doing. And our main variable of interest, again, is going to be in the labor force. Okay? Remember what we were doing before. If we had wages and we logged them, we threw some people out. Now we're not going to throw them out because either you're working or you're not. Okay? We're going to look at non-wife income, education, experience squared, and husband's wage, along with age, kids less than 6, and kids greater than 6. Okay? These are all things that might determine whether, in this case, this is females aged 30 to 60, and by the way, notice the date, just in case. Anything that comes out of it is not my fault. But basically, we should be able to see some information that determines whether the woman is in the labor force due to some of these determinants, hopefully. Okay? Let me see if there's anything else. Yeah, and then we're just going to estimate a Logit, Probit, and LPM model and just sort of compare in general across for right now. Okay, so actually I was using the panel the other day because I was using the Mirage data set. Sorry, I forgot to actually say that yesterday. Okay, so we're going to be using the Mirage data set, and from this we should be able to see the information once I pull it up. Let me just do this. There we go. So yeah, you can see some of the outcomes that we're actually looking for here. So we can, in the labor force in 1975. Oh, sorry, this isn't panel. My fault. My head is stuck in tomorrow. That's why I'm confused. Okay, so yeah, this is just the cross section. Okay, so basically the kids less than 6, just to give you some information, we're just looking at the number of kids that somebody has that's less than 6 versus those that are between 6 to 18. Years of education, wages, husband's wages are out. Oh, that's hours. Husband's wages, yeah, at the bottom after that. I mean, I could be very detailed. There's a lot of things in here that we could say will be determinants on this. You know, education, your education versus your husband's education. We could also include family income. Also, there's some, I'm not sure if he's going to use those examples, but we could use mother's and father's educations to help with any type of endogeneity. But those are all possibilities. So let me go to the code real quick. You're going to notice that it's not that different from the code that we had a second ago that I was showing you. Basically, we have the GLM. We set up our equation across. And then basically we're defining the family like we did before. In this case, the first one's going to be the Logit. The second one's going to be the Probit, and in terms of the third, standard OLS. And then we just basically produce those outcomes, and when I produce it, let me just open it. Take a second to run. Yep, don't want to look at this in tech. Give me a second. No, it doesn't like HTML. Hold on. Give me a second, and I'll have it in a second. Oh, that didn't help. There we go. So in this case, if we're looking at non-wife income, we can see again, like I said before, they should all agree. You know, they're all going to tell you exactly, is it decreasing or increasing the probability of success? Or in this case, viewing that particular woman in the labor force. Okay? In terms of education, we see that basically they're all positive, meaning that that has a greater likelihood of actually being in the labor force. Experience is a little non-linearity in terms of, you know, experience, and we expected to see that. In terms of husband's wages, kids greater than 6, we don't see any meaningful impacts. Okay? Then we have age, and kids less than 6 have an effect and basically decrease the likelihood that you view a woman in the sample in the labor force. You also notice that basically, remember what I said before, that before we were taking the log and throwing out, say, a little over 200 people. Now we're actually keeping them in. So now we have 753 observations. Okay. Other than that, I don't believe I calculated some of the stuff that we're going to show later, but let me check. Yeah. Yeah, I didn't actually report some of the measures. There's some information here that helps you in terms of the log likelihood that you can use to see how well the performance was. There's also something I'm going to show a little bit later on called a pseudo R-squared. That is not an R-squared in the same sense as what you know. It's meant to be more of something that it gives a measure of how well the model fits, but it's not like what we think about in terms of how well the one line goes across all observations. Okay, so we'll talk about that in a little bit, but basically this is exactly how you would run it. This is why I was saying it's not necessarily the best example, in the sense that it's basically just repeating the same thing. We're just changing the variables a little bit. But just note, like I'm saying, keep this as very start to sort of give an idea, because if I was looking at this and my coefficient that I'm looking at, like I said, in the LPM, should be very similar in terms of, direction at least. If I run that and then I see I expected a positive outcome, it should help basically or increase the probability of success. But when I do the LPM, the coefficient is negative. I could have done that with the Logit, but it might take a lot more time, or the Probit with a lot more time. It might be good to just do a quick check first with the LPM and then move on to the more advanced models. Okay? That way it might save you a lot of time and effort. Other than that, like I said, it's pretty straightforward unless I'm missing something. Is there any questions over this? Anything that surprises? Okay? And remember what I said. This relative to this is meaningless right now for us. I mean, it has meaning, but at the same time, we can't do a comparison across. Even though this is quite large, so what? You need to tell me how that large effect is relative to actually affecting, this is the Logit, affecting the log of the odds ratio. Okay? So you can use it, but please don't try to do any type of comparison that is large or small or anything like that. Because right now, that's not a part of anything that we can see. Okay? Was that the only thing I asked to do, was just to... Oh yeah, when I originally was going to do this, when I said compare output across, I was expecting somebody to look at those larger numbers saying it's larger here, larger there. I guess I was trying to trick you a little bit. But yeah, just sign, nothing else. Okay. Okay. Quick, easy, practical. Okay. Okay, so this is where it starts to get harder though. We have the estimates. Now let's move on to the marginal effects. This is where too many choices. But even with all those choices, it's your research. You know it better than anyone else is supposed to know about it. That means you know what the interesting points are within your data. If you're just going to take it and do the averages and not really try to examine, more particular things about your data, more interesting points, that's up to you. But a lot of times you want to go a little bit beyond just looking at the averages, because that's exactly what we can look at in this case, that basically it's no longer just one coefficient across everyone. We're getting more into that realm where, remember, we interacted things and we were able to see it actually varies across how much experience you have, what your level of education is. And we can do the same thing here. Okay, so that's where these models benefit us in that way. But that's where we have to actually take it one step further. So we know the sign is helpful. And we can actually compare those across our these three types of models. What about the effects on the average individual? So that's where we need to make choices about the reference point. Do is my research, say, from the older example that I had, is it about people that have at least one child who is less than 6? Is that a really big barrier for someone being in the labor market? Is it something about their education going from at least matric versus basically dropping out, say, at 11th grade? Okay. How much is there a difference in the probability that somebody's employed just because they take one additional year to finish? Okay, these are all things that basically give us ways of looking at more uniqueness within our set. Most of the time we just report the coefficient and say that's the effect and that's it. But here we have a few more choices. So the marginal effect is going to depend on the evaluation of xi. If I set everything to 0 and I only look at education, that would be me assuming that every other characteristic for some reason is set to 0. I wouldn't really know what that means for the person because, you know, I mean, you'd have to think about it in terms of would anybody ever show up with those type of characteristics? Okay? So there's your choices are going to kind of change on how you think about the person or the whatever the unit of analysis is in your data set. Okay? And in that case, everything that goes inside of this function is going to be important. We have to evaluate it. But we have to choose the evaluation point. And then once we have that, when we actually take the derivative of that probability, it's going to be the coefficient on the variable of interest that we're looking at. If it's education, if it's experience, if it's kids less than 6, that's where this particular coefficient is coming from. Okay? The next set is the evaluation of the entire linear function into the link function that then we put into our probabilities. Okay? Or into our PDF. Okay? This is what I meant by there's additional steps. Coefficient helps, and this is why we can sign it, because basically the sign of this marginal effect is whatever's on the coefficient. Once we have that, everything else that we choose is going to go in this function, and then we have to turn it into or to evaluate it. So what evaluation point of x's do we choose? I might have an opinion on it. You might have an opinion on it. And I can tell you that when we present these types of models, basically we're presenting and we have to make an argument for our choices. That argument either will sway the audience or it won't. They'll come back and say that you need maybe, what about this? What about this? Those are evaluation points as well. How strong you make those arguments is basically going to say how many times they're going to say, what about this, sort of? Because if you're not influencing them very well, it might be just random things they're asking, or it could be trying to help you. So make sure you you have a good argument for why you chose that particular point. Okay? So we can evaluate these marginal effects at the sample means if we want to. That's fine. Sometimes we only care about the mean. I shouldn't say or this time. So we're basically capturing the average individual. Also, we sometimes call this either the marginal effect or the partial effect at the mean. Okay? I try to make sure that I'll either, at this point, there is a little bit of differences, but from this analysis, usually we can kind of group those together. So that's one evaluation point. Compute the marginal effects for each observation and then take the average. So I give everyone their particular characteristics and then calculate the propensity score for each of them. And then I take the average. So those two choices is one taking the average prior to my calculation. The other one is taking the average after my calculation. Once I do that, basically I'm going to multiply it by the coefficient of whatever my variable I'm assessing in this case. So those are the first two. These are the most likely for your choices for most people. Then you can then choose the evaluation point that aligns with what your research question is. If you're looking at the overall income distribution and information, you have the entire, we'll say a random sample of this information on whether somebody's working or not, all their information, but your project is very specific for people that have been out of work for a particular length of time, specific gender, racial groupings, areas. It could be a lot of different things. Then you need to choose possibly characteristics that are more aligned with those that population. Okay? That means it can become very specific in this. And this basically can be a little bit of an issue sometimes, because sometimes I know that you're going to most likely, as soon as you saw marginal effects, you went into look for R and for a program that does marginal effects. That's typically a problem because basically that command is given examples most time, or well, at least examples you find typically will focus on the first two. You have to make sure that you're doing it the proper way to actually try to do the third one. So that's why I usually suggest people try to do it by actually working through it instead of trying to use a package or a command to do it for you. Because every student that I know so far that's shown me when they use Stata maybe or something, and they use the margins command that most people have probably used before, I've never seen a student use it right yet. Because they just type in margins, dy, dx, and then they put the variable, and that's it. But it's not the question that might be asked. It's that one, in that case, would be the second one, if you did it in that format. Well, actually, it would depend whether the variable that you're under consideration is either binary or categorical or continuous. It depends on what it is. That's why you have to know. So if somebody tells you to go and do the marginal effects, you need to know what that particular package is doing. If you don't, you can get into a lot of trouble very fast. If you're presenting this type of work, somebody, and you're going to show the coefficients and you're going to say this is the marginal effect, they're going to ask you what marginal effect, which point did you choose? You need to know that. You can't just say, I ran the command, I used the package. They're going to stop listening to you very quickly because you're just using packages without knowing what it's doing is problematic. Okay? Because you're in there for a particular reason for this research, and you need to know if that answer, if you've calculated, or at least you attempted to calculate it correctly. So just keep that in mind. Make sure you understand how to do it first before doing the easy way. If you know how to do this, and then you run the margins package or margins command, whatever it is, and it gives you the same answer that you got, you're on the right track. That means you can use it because you're getting the same answer. And that's where the packages actually will help. Once you know if you're getting the right answer, those packages can then help you create standard errors for those things using either Bootstrap or other types, delta methods, or confidence intervals. They can also help you graph them across various other variables, which is possible. But again, you have to make sure that you know what it's doing first. Because again, I've not seen a student yet do it properly. Well, let me rephrase it. PhD and above, I've seen it done properly. But I've seen them also make mistakes too. Okay? So your chosen evaluation point will affect the magnitude and interpretation of the marginal effects. Each little change in which evaluation point you're choosing is going to give you different insights on the impact of that covariate. If I'm looking at the old one, or the other data that we were just looking at, if I'm comparing people with kids versus people without kids. I'm going to get two different probabilities, right? That's the comparison I want. And this sounds mean, don't pick them, but basically how much of a barrier is it to employment if you have kids? Okay, so those are things that basically will give you slightly different impacts here. So that's some of the things that we want to compare. Okay, so I want to make sure everybody's really clear on this. Okay, valuation point matters. Okay. Okay, look up from your computer. So you're good on that, right? Okay. So if we want to give you more of the mathematical expression, we can basically write it out as the average marginal effect in this case. See how basically it's running the calculation, doing the calculation, but then we're taking the mean at the very end. In terms of the marginal effect of the averages, we're basically setting the mean at the beginning and then doing the calculation. So in most cases, they're going to be very similar for well-behaved data for the most part. They can get some differences. Okay? And then the last we need to kind of keep in mind of as well, it still applies for both of these, but when it comes to discrete variables, discrete, there is no marginal effect in the sense of the first two here. What we'd have to actually do is calculate the CDF of each of these particular, when you have it at 1 versus when you have it at 0. Once we have that, we take the difference, and that would be our the marginal effect for a dummy variable. Okay. If it's the average marginal effect, we just have to basically, actually, sorry, what am I doing? Well, yeah, since we're doing it for a dummy variable, I shouldn't say it that way, but if we were doing it for the marginal effect of the averages, we would be setting the averages for all the other outcomes, because that still plays into a part of the difference between the when it's set at 1 and whenever it's missing from the regression. In terms of the other, we would have to think about it as giving everybody their values, but then taking the calculation at the very end. Okay. But what about something like education? Which one does that fall under in this? Depends on how you see it. Is education continuous or is it discrete? It's not really a dummy variable, but if it is in some ways a category, then basically I could say that this, if I was wanting to know the difference between having matric versus not, I could think about this as being set at 12, and then this being set at 11. And then it's discrete difference between it. If I made the assumption that it's actually continuous, which some people do, then I'm making a choice between the top two. So it matters sometimes how you actually see the variables as well. And we do that, but sometimes we're very cautious about doing it. Yeah.
Yeah, because my thinking here is that you can't really have a binary in education really, because
well, it's not binary, but remember we were always combining, we had binary and then we talk about categorical variables, right? Then there is no 11.5 that we view most time, right? We view 12, not 12. Okay? So in that case, it's not binary, but the jump is discrete. So that's why it matters. You know, in that case, if somebody asked you to do the difference between 12 and 11, you would want to use this function. If they're just saying, what is the outcome for the average marginal effect of education, and you just say, assuming that it's continuous, if you assume it's continuous, then you can actually do this one. That's what I'm saying. Just be careful about how you're describing your variables. If it's discrete, you can actually be, you can think about it in one way, but somebody else will think about it another way. That's why I'm saying you know your data better than other people. That's why you have to make your arguments about how you see those outcomes. Okay? So this is how, in general, we think about the marginal effects. But we really haven't went into a lot of details yet about how we go about them. So I just want to sort of do an example with this. Again, same data, just sort of being repetitive here and talking about it again. But this time I'm going to throw in some descriptive. I didn't show you the descriptive statistics before, did I? Oh, okay, maybe that's new. But we can think about it as terms of all the variables. We can think about how, so this would be the basically 56% or 57% of the women in this sample are in the employed. We could also think about how the other income, education, experience are. Are they very similar? So if we look at the not working versus the working, we can see in terms of education, typically for working, the education is slightly higher. In terms of experience, also not just slightly higher, but higher. And we could keep going through to do a slight comparison. But the funny thing is, if you look at husband's wage, that basically we actually see that there might be another reason why they're not working other than, education. In this case, it's kind of funny that the reason I'm looking at that is because in the other regression that we ran, husband's wage didn't matter. Or at least, let me rephrase that, it wasn't significant, at least in the Logit and Probit. Okay? And then we have age and children, typically not working. It's not 0.3 children. It's basically, either 0 or 1, 2, or 3. So basically, but the average is higher for kids less than 6 for people not working. And for kids greater than 6, still a little bit higher, but not really a big difference. We wouldn't be able to say there's a statistical difference between them. Okay? But this is something that you need to know before when you're working with these. So basically, you're looking at two groups here and you want to see what might be determining those outcomes. The same regression that we ran earlier, I believe. I don't think I made any adjustments. Yeah, I think it's all the same variables. I don't think I removed anything, so it should be fine. Okay, so this is nothing different from what we had prior to this. And so what I'm going to do is I want to kind of go through sort of an example with this and see how we might go about calculating, in this case, what is the marginal effect of education in the Logit model. I could make you do both, but basically it's going to be very similar for most cases. So the marginal effect of the averages or the average marginal effects, or another interesting point. So if somebody goes about telling you, or supervisor, whoever, ask you for what's the marginal effect, what is the effect? You need to be specific. Which one do you want? There are many. Too many in some cases. So in that case, you ask the question back, which one do you want? Then they say you choose, then you go, but if it's your research, make sure that you choose the point that is trying to drive your particular goal for your research. And then in terms of education, remember I told you consider it continuous, depending on how you look at it, or you can consider it discrete, and we could actually get many different probabilities over different levels of education. Okay, or differences between levels. Okay, in terms of the average, what we're going to do is basically, I'm already putting some numbers here, but I'm going to show you how to do it as well. Basically, we take the coefficient on education. In this case, for the Logit, it was, I should have pulled that out. It's 0.222. And we're multiplying it by the sum of all the propensity scores that we have divided by the number. So we're just taking the average at the end, and it's going to give us a change in the probability. So moving, if I'm considering continuous right now, I'm just assuming, then it means the average marginal effect is going to be an increase of 4% probability that the person is working. Okay? If we evaluate it at the average coefficients, basically this is another calculation. It's just that we're using the means inside of this function so that we take it at the very beginning. Then the effect is a change of 4.7%. Like I said, they're going to be very close for the most part. It's just about where you're taking the average. The reason why people usually prefer this one here is because of the statistics I was showing you just a second ago. When you give the average across the population, then the person's education will be set at 12.28. Given that it's discrete, who is that describing? Person that just finished matric or somebody that's going into college? Okay. When you look at age, are we actually seeing people on our data set that are 42.5 years of age? It's possible, but it's not how it was recorded. Typically, we'd have some other things in here, but how many of you have 25% of a kid? Things like that. So technically, what we're setting these at for the averages before we do the calculation is that really representative of our sample? Because remember, we're trying to describe somebody within our sample. So some people are picky about that. I've run into a bunch of them. But if you look at, like I said, if you look at the difference between the probabilities of the calculations, it's not huge. Okay? So most time you're going to focus mostly if you're doing at the averages or what they call the average marginal effect, you're going to be using this one because they for some reason are very picky about whether this really is representative. Typically also if you have a lot of in surveys where we know only particular things about people, whether they have children, whether they've worked in the last week, male or female, other characteristics. What happens is when you have all those types of binary type characteristics, then you take the average beforehand. If you're looking at gender and you basically have more females than males, and you're looking at somebody that's 0.6 female. It's not representative within the sample. That's why some people get really, or they basically point out that you need to choose a different point. But in general, just like I said, just be, go with what the literature is doing in this case for you. I'm always going to point back to the literature because each literature is going to have their own which one they prefer for whatever various reasons. And then for the discrete change in education, I just chose between 12 and grade 13. If I calculate the CDF, in terms of those at 11, I get 0.57. In terms of education at 12, I get 0.61. That means if I take the difference between the two, the change is 4%. These are all answers that could work. And you notice that, these are only 3 of a possible many that you could use. Okay? That's why when you're doing this and you're doing your papers or your presentations, things like that, it's your job to tell the audience or the reader why the point you chose is important. Why is that the interesting part or question for your paper or your research? Okay? Now we've shown this, I'm going to show you some of the code behind it. Just make this as wide as possible real quick. Okay. This is what I meant by it's a little bit tricky to do this. Now, I'm taking a lot of shortcuts, okay? What I'm going to do is I'm going to show you this, but I'm also going to show you an easier way to think about it before you start doing these more advanced ways. It's basically a way of me of saving some time in certain areas. That's the only reason. But basically, we have to set up the model and get all the variables in the right format. So in this case, I used the log of non-wife income. I need to make sure that I have the experience squared, and then I just, get the data set down to what I need. In this case, I need to go through and calculate the means for the full sample. That's all this is doing here. And I also get the standard deviation of them as well. And in terms of, I should be particular about this. This is only for the summary stats. Okay, so I'm just basically showing the full sample versus the not working versus the working. So I'm just trying to take the means across so I can give you some information. Okay, once I have all this, basically I can put it in a table, that's fine. The reason why I try to do these calculations ahead of time is because I go back and use these. Because if I'm having to calculate the mean for the partial effect at the means, I need to know what it is so I can feed it into my regression, right? Or feed it into my probabilities. If I'm doing it the opposite way, I need to do just the values, but then take the mean at the end. So I typically will do this at the beginning. And then once we have that, sorry, let me go down a little bit. Remember what I said, you need to take each of the coefficients you got, and you're going to need to multiply them by either the variable that you're looking at, or the variable, each of its covariates, or you're going to need to calculate the mean and then multiply that by the coefficients. So one of the things that you need to pull out here is the coefficients from the Logit. Okay, there are smarter ways of doing this. It's just I chose this way. It's creating new numerics here. Then for the first one, I need to take the means of each of these, right? So basically making sure that I have the mean of each of those, my covariates. Notes, remember how in most programs you're using, you have to tell it, it knows not to use NAs? Remember I told you that R, you have to tell it everything. That means if you try to run that without the NA remove, it's going to say that no value exists. Because if NAs are in there, it's going to say, can't do that. So just keep that in mind that you need to remove those NAs. And then look at this function here, prob 0.1. It is the Logit's constant plus the Logit's coefficient for, I called it family, sorry, I should have called it husband's non-wife income, I think it was. But I had to multiply that by the mean that I calculated. Oh, which one is this? Let me make sure I'm right on here. Okay, I got my ordering mixed up here. This one actually is the average marginal effect. So I'm actually going to multiply the coefficient by the actual variable. So whatever your variables are that you have, I'm going to take that coefficient and multiply it by yours, and keep going until I actually get a value. Okay? Because I'm looking at grade 11 versus grade 12, I actually have to multiply that coefficient by 11. And then you're going to see same with the coefficient from the experience, multiplied by itself, by the variable itself, experience squared, and so forth, until we estimate the model. Remember I told you it's a linear outcome before we plug it into the function. So that's why we have to actually calculate the prediction. Now remember, I told you there's an easy way to do this. We could actually have just said predict this outcome from the actual GLM command. But remember what I told you before, that just doing a prediction is going to do everybody's values that you have. But it wouldn't be able to pull out this, that I told it to also include that the outcome for somebody in 11th grade, right? It's going to give you the prediction and give everybody their education values. So that would be the difference between this and using predict in the GLM command. Okay? That's why I said you have to know exactly what it's doing. You could do a little bit more by the packages, but just making sure you're clear on that. Whoops. Okay. Then for grade 12, I go about the same process and just throw 12 in there. Now this thing right here for this person or this calculation is specific. I give everyone their individual covariates, but I force everyone in this portion of the sample to be at matric, everybody in this portion to be at grade 11. Okay? And then for if I want to do the same thing, but this time I wanted to give everybody their means, I basically take those calculations I did for the mean and multiply them instead by the coefficients. Okay? So you can see that each method is a little bit of a change. Okay? Come on. Once I have all those calculations, same for that last one there, prob 1.2. What I need to do now is, remember, I need to transform it, that linear outcome, into a the log odds ratio in this case. So I need to take the exponential of the calculation and take that calculation and divide it through by 1 plus the exponential. And then take the mean of that. And then I can do the same thing for the other calculation, but this time, this case, I'm going to take the so I'm going to pull out the probability in terms of the mean itself again. And then this is a separate one for when I'm going to take the average of the covariates. Once I have that, I can finally get to my answer. Which answer 1 is basically the coefficient. Remember, you need that on education. Times improb 1. In this case, this one here. Okay. Answer 2, whenever we're looking at if we're considering, again, continuous, big assumption there, then basically I need to take the coefficient and I need to take the probability 2 times 1 minus probability of 2. And then for the discrete case, I need to take the CDF at 12 versus the CDF at 11. This is exactly what was showing on the other slide. Okay. Now, if you understood all that without me having to go into more detail, good. But given the look on most faces here, there's some questions. So throw them at me. Okay, so let's try to go through some of the steps here. Why? Okay, so which part really just started saying, in your head, nope, 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 nope. So we do know that, remember that what's inside that function is some type of linear representation of what we got, right? So we know we need to take the coefficients, multiply it by something. Okay? Yeah.
Okay, like my question lies in the lines of, for an example, in this case, what we were dealing with Probit. But if I intend maybe to use ordinary logistics equation I'm looking at the relationship size based on ordinary, given that my literature was derived, rather my literature was highlighting all of the ordinary, then the kind of data that I'm using correspond with the literature. So I can getting to find shepherd cross tapes, and then to enter results and
So you're talking about an ordinal model, right?
yeah,
Yeah, so that's going to be order. That's going to be later today. Right now, we just want to understand that we need to understand the binary version first to get into the next step. But this is that part that usually. So remember that each of these is for a different calculation. This one is for the average marginal effect for a person at grade 11. This one, well, let me rephrase that. This is to get that inner portion within the function first for a person at age or grade 11. This one is for the inner portion of that function at grade 12. Now, if we're treating them discrete, remember that we need to know the differences between the two. We need to calculate the CDF. So that's where these calculations come in. For this one, we're basically taking the marginal effect of the averages. Remember, it's about where you take it. For the average marginal effect, we do it at the end. That means we're not going to do it inside the function, if you want to call it the G function or whatever, but if we're looking at the logistic, it's in that the logistic function. Okay, so that would mean that we're taking the mean first and then calculating. If it was the other way around, we would give everybody their value, then we would take the mean at the end. So this one is the setup for the discrete version of this. This one is starting the setup for the marginal effect at the averages. Okay? The key is here is to get what's supposed to be inside the function first. Don't focus on anything else. If you're going to do it at the means, make sure you get at the function first, or you calculate everything in the function first. If you're not going to take it at the means, but later, to calculate a numerical value for everyone, you're basically creating a new column that says this is your score, or this linear representation of your score at your values. Okay? So in that case, these are two different versions, and then you have the one that's with the means. Once we have that linear, remember the x beta, once we have that representation, then we need to figure out how to feed it in to get the actual probabilities. And we need to push it into the link function. In this case, if I was doing it for both of the, in this case for these two, kind of leave out this one for now. These two are for the discrete. This would give me the CDF outcome for 11th. This would give me the CDF outcome for 12th. Okay. So after we've done that, we can basically throw these aside. So that's for the discrete case. But when we do the average marginal effect or the marginal effect, or the average marginal effect or the marginal effect of the averages, we need to take it one step further. We need to actually feed it through to get the PDF. CDF is okay, but now we need the PDF. In this case, we know sort of what that function looks like. Basically, it's the probability times 1 minus the probability for the Logit. And then once we have that, we have basically the average derivative across the sample. Okay? Same for, so this is 1. And then we can actually feed it into the logistic here to get the probability of the averages for education. Okay? And then we're using that information for the continuous marginal effect, or the average across all observations. This is that calculation. So it's beta times the calculation. For the average marginal effect, it's the coefficient times the PDF. So I basically took a shortcut here that, instead of recalculating this here, I just put it here. Okay? And then for the difference in that discrete outcome, then basically it's just a difference in the CDFs. So you're starting to see why when you start out this, it looks fine. You can run the regressions easily. That's not the problem. It's getting what it means at the end of it. Okay? So this is what I sort of want you, we're going to practice a little bit after the lunch break, because this is where most people falter in what they're trying to do. Okay? I know it sounds weird right now, but if you get this down, basically you can talk to anybody about what is the changing probability in terms of either the average individual or the average across the sample, or basically a point of interest. So in that case, I didn't show this portion yet, but we'll kind of go into this as well. That this is sort of how you're basically looking at how well did I do? Was my model doing well, or was it just didn't work at all? So we're going to talk about thresholds as well as in terms of predictions that are, or how to calculate the percentage of correctly predicted outcomes. Because this is going to be our new pseudo R-squared. Basically, did I do well enough to predict 50% of correctly for my sample? And is that even good? That's like a coin flip. So we're going to need to talk about the thresholds as well. Okay? So that's how you go about doing the same calculation. So remember, the key is first you need to calculate the linear outcome within this. That's where we're using those coefficients and the covariates to basically get our linear prediction. Once we do that, we need to feed it into whatever function we're looking at. In this case, the logistic. And then once we have that whole, then all we need to do is multiply it by the actual coefficient. This is what I mean that you can't just look at the size of the coefficient when you run the model. Until it's fed through all this, it has no meaning. Okay? And then this is where we need to sort of do a little bit of information as well in terms of goodness of fit. Basically, there's not one. There are many. There's some standard ones that we use, and there's some non-standard ones. So one of the ones that we can actually use is we get a prediction. We get a probability of the outcomes. Once we have those, once I choose a threshold, let's say it was 50%, that means if the probability is above 1 and they're working, that's a good match. If it's less than 50% and they're not working, that's a good match. Anything else is a bad match. It means it's a mismatch, a misclassification. Okay? So that's where we can do, one is percent of correctly predicted. It's just we need to choose a threshold. Is 50% a good choice? It depends. What if my sample, my binary variable, what if everybody in the sample is working and 75% of them are working? That's a proportion, right? But I'm only using 50%. Maybe I should be using 75%. I should try to match the proportion that's in my sample. That's going to do a little bit, that's going to make my work, or it's going to make it look like my percentage predicted correctly is going to go down because I'm raising my threshold, but it's a lot more accurate. Okay? But I could also choose 20%. And then everybody would laugh at me for choosing 20% if the sample's proportion is 75%. Because that's just going to be over-correcting and make it look like my sample does my predictions are very good. So it's a choice on your part, but usually you need to pick a credible threshold. In this case, a lot of people do choose the proportion within their sample. You can also use the McFadden version. There's a few of these, but generally this is how they're set up to where you use a constant only model. It's run, and that gives you a likelihood. Then when you actually run your model, remember, it's a log likelihood. So we're, instead of being between 0 and 1, it's between 0 and negative infinity. So what's happening is you start off at one point with your constant only, how well it defines your probabilities. And then once you actually use your model, it's actually it's actually increasing and moving towards 0. And what you're actually going to look at is 1 minus how much better you did from where you were in the constant only model versus where you ended up. So how much more did I actually, how much better did my model do over a constant only model? So if I was actually do one of these two, in my case, my threshold of being within the sample was 0.568, then my percentage correctly predicted was 73%. It's not bad. But again, it's not one of those cases where you're always going to have a high R squared. And it's not always the case that this is going to agree with this. Okay? That's why they call it pseudo. It's trying to do the same type of job, but it doesn't guarantee that it does. Okay? So there, like I said, there are other measures of goodness of fits. These are the two that I usually focus on. This is also a way of actually estimating the a pseudo R squared for quantile models that we were showing yesterday. We can look at the correlation, or the square correlation between the predictions and our actual values to get a pseudo R squared as well. In these world, we're always dealing with pseudo R squares. But it is telling that, you know, if you say that this is a good model, but what if it's not predicting correctly for people or the unit of analysis, whether they had a 1 versus 0? So that's where that comes in. It's telling you, it's like if you were placing bets and I know how often you won versus how much you lost, and, you know, how well was I actually viewing your activity and saying that, you know, I'm doing a very good job in predicting whether he's winning or losing, right? That's what we mean by this pseudo R squared. Basically, it's telling you how well your probability model is doing in picking whether or not the population you're actually observing probability of success accurately, or it's doing a poor job at predicting that. So that's why it's beneficial there. So that's why there's so many of these. We basically are finding ways to maybe make adjustments, and we do it. But again, even in the case of this, even when I've done this type of work before, I've at least put 3 different versions of these outcomes. Like I know there's the McFadden, there's the correctly predicted, and then there's one that's just not popping in my head right now, but it's also one of the standards that we use. So I would definitely at least use a few, especially if they're very different. But you can put the best one at the top if you want. But hopefully they see that one first. And then the question is, should focus be placed on statistical and economic significance of the explanatory variables? Remember what I was saying yesterday, that there's a control is just a control, but it's meant to be in there either due to theory or past research, and it might not be significant. But its removal definitely will affect, will affect what goes into this. Its removal, right? Once it's removed, everything changes. Remember I was telling you before that if you add another year, if you change your sample at all, everything changes. Same applies here. You're changing that relationship within the set. So there are tests, just like we do with t-test, f-test, but they're just slightly tweaked most time. I mean, well, actually they're, because MLE is, under most properties, is consistent and asymptotically normal. We can actually use the t and the f. But we still need to go through that and make sure that we're actually removing something for the right reason, not just because we want to see a bunch of stars. Okay? So keep that in mind. Because as soon as you do that, everything in this side changes. That might be very similar to what it was, but that might have a huge change, but I would also expect the coefficient to change, which changes that relationship. So the R squared is in some ways related, the pseudo R squared is sort of related to this, but it's, so it's more, so that one's based more on the probabilities. It's not actually based on the, this calculation. It's sort of more on this side here before the additional stuff. So we're going to be looking at, you know, our propensity scores and then how well, after we choose a threshold, was it good, bad, you know, stuff like that. Okay. But in the practical, I'll kind of go through it and we'll kind of give a really good calculation of it, and then we can kind of see how we calculated it. That might be, I mean, we do all this, but then it's that hands-on that really gets you to see it in your head exactly what you're doing. Because a bunch of symbols up there might be meaningless to you until you actually see this is this step, and this step, and then this step. Okay, so we'll go through that. Yeah.